Yes, so today's purpose is to really solidify everything we've been doing with rate problems, and so we can actually start with homework questions if you have.
Yeah, how 2006 number 2.
2006 number 2. Let's pull that up here.
And question C. I looked up the answers, but I still didn't get it.
Uh-huh. Number 2. Yes, this was a challenging problem, and I think the scores on this problem are probably pretty low. So we have cars turning left at the rate L of t, and the graph is shown above. Now this isn't really a rate in, rate out. This is just a rate turning left, so that's okay. To the nearest whole number, total number of cars turning left at the intersection over the time interval. And so in part A, we have a pretty straightforward total equals integral of rate. And then we're going to get some number on the calculator. You know that number off?
1658.
Okay. And that's after you round, right? Okay. And then in part B, they ask, traffic engineers will consider restrictions when L of t is greater than or equal to 150 cars per hour. Find all values of t for which L of t is greater than or equal to 150, and compute the average value of L over this time interval. Well, greater than 150 means that L is going to be above this line right here. And so if I let y2 equal 150 and set equal, then I find two intersection points. What were those two intersection points?
12.4383 and 16.12.
Okay, that works for me. And now I'm supposed to, so in terms of what I need to show, I would show L of t equals 150, t equals those two numbers, 12.4383. And 16.1212. And now I need to find the average value of L over this, and this is a simple matter of averaging. One over b minus a times the integral from a to b of L of t. That turns out to be a certain average number of cars turning left per minute. What did that turn out to be?
199.4263
Cars per hour. That's a lot of cars if you stop to think about it. This means more than 10 cars, about 15 cars per minute or so. Yeah. Sorry, more than 20, right? Yeah. About 25 cars per minute. That's what I was meant to say here. So you take 25 cars per minute, that's like 1 every 2 seconds.
So is this the whole answer for B?
Let's see. Good question. Did I find all the values of t? Yes. Did I compute the average value? Yes. Did I indicate units of measure? Let me check. Cars per hour? Yep.
We need to write like the LT is greater than 150 when t is greater than 12.4383 and less than.
I see. Yes. So you're right. My answer would be a little bit incomplete because I did not answer that question completely. Really, I should say that L is bigger than 150 when t is between these two values. So I agree with you. Yep. Now in part C. Part C was, yes, traffic engineers will install a signal if there is any 2-hour time interval during which the product of the total number of cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000. In every 2-hour time interval, 500 oncoming cars travel straight through the intersection. Does this intersection require a traffic signal? Explain the reasoning that leads to your conclusion. Very interesting question. Let's see if we can unpack it. Do you see any math here that I can use to unpack the question? First of all, we have a decision to make, and our decision is traffic signal and no. And so we need to find the decision criterion. Where is that decision criterion?
I just don't get the first sentence.
Okay. Are there any words that you don't understand?
I don't understand the sentence. It said the product of the total number of the cars turning left and the total number of oncoming cars traveling straight through the intersection is greater than 200,000.
Okay. So let's take and break that down. That is the criterion. And you notice how we see that it's the criterion because they use the word if. Okay? So we have to determine if this is true. And what we're looking for is for the product of total number of cars turning left and total number of oncoming cars traveling straight through is greater than 200,000. So let's translate that into math. What does the word product mean? Here's our problem. What does the word product mean? Anybody? It means the result of multiplication. So, what they're really saying is that left times straight has to be greater than or equal to 200,000. And so if I translate that, times total straight this is our decision criterion expressed in math. Does that make sense? Yeah, so it was the word product that you actually didn't know that was tripping you up here. And they also tell us that the total straight is 500. Which means if I go ahead and divide here, now something's bothering me. Oh, we're good. Okay. That means that the total turning left has to be greater than or equal to 400 during that time interval. Now, this is not the L of t, this is the total left. So I actually need to find a 2-hour time interval during which my total left is going to be 400. What's my best bet? Right, something around the max over here. And the max looks like it's around 15. So let's take the 2-hour time interval from 13 to 15 and see what happens. This is my best shot at finding a 2-hour time interval here. And when I integrate, did you choose 13, 15 also?
Yeah, it's 431.9.
Yeah. 432, which is greater than 400. So the answer is yes, we will.
So we always find the start of the max, like you had in your question.
Well, I don't know about all of this, but for this problem, we were looking for the total amount left to be bigger than 400. And so I went and looked for the greatest possible number here, because that gave me the best opportunity to find a total number greater than 400. Does that make sense? Yeah. This, by the way, is a lot more sane than what the state of Maryland appears to do, which is to let an intersection go until somebody dies. I believe that is actually their decision point for putting a line in, at least it appears to be now.
Do states actually use like the products of two, like?
Yeah, that was an
Because that's-
interesting
yeah.
decision thing, but it makes sense, because if you think about it, your chance of somebody getting broadsided is equal to the probability that one person is in a location at the same turning left, while another person is going straight. And that's going to be proportional to the number of cars present. So this actually makes a whole lot of sense, expresses probability. Yeah, really good question.
And I know you want us to like check them all and stuff like that. Would you like us to go back and, correct mistakes we make, or if we?
I would say the decision point would be this: if you got less than 6, you should definitely go back and work this a second time. If you're getting between 6 and 9, I would say, okay, that's some mistakes I made, let me move on to one.
Okay.
And the reason I do it like that is if you're getting less than 6, then you're gonna have multiple mistakes. And you will not internalize all the corrections. Whereas if you're getting between 6 and 9, you basically like missed one thing. And you can check it off. Okay. Any other questions before we take a look at our problem for today? Okay. Let's take a look then at problem before you, which is 2009, number 2. And we look at this in a pretty straightforward rate problem. What I'd like for you to do actually is to get out one piece of paper and calculator and take 15 minutes to do this problem. And then we will talk about it together. If you are following along at home, let me encourage you to do the same. Get a blank piece of paper and calculator. Give yourself 15 minutes. And we will pause the video, come back when your 15 minutes are up. Let's take a look. So, the rate at which people enter an auditorium for a rock concert is modeled by the function r, given that RT equals blah, blah, blah. This is a rate in. And there is no rate out. People are not trying to escape the concert. And the initial value is?
0.
0. That's right. There's nobody in the concert. In reality, it'd be like 10, right? That one guy that shows up 4 hours before the concert. How many people are in the auditorium when the concert begins? This is a pretty straightforward calculation. The number of people is going to be the integral of the rate from 0 to 2. And that number turns out to be, I believe it was 960, is that correct? 980. Part B, find the time when the rate at which the people enter the auditorium is a maximum justifying answer. A lot of students will miss this question because they try to find the max of the wrong thing. So we want to pay close attention to the thing we're trying to find the max for. The max, they want the max of the rate, and the rate is RT. So we need the maximum value of RT. And that means that we need to consider the critical points of RT, which are found by setting the derivative r prime equal to 0. And r prime is going to be equal to 0 when r of t itself has horizontal tangents. Now, this is kind of an interesting thing, and I want to talk about this a little bit. This is a graph of r of t. Let me change the window size just a little so that we can, so that the integral will go away. So here comes r of t. That's the w prime from the other one. And the thing that I want to talk about is this. My calculator can tell me the maximum value of this function. If I go to Second Calc Max, Then it will find the maximum of the function with a left bound of 0 and a right bound of 2, and a guess somewhere around maybe 1, and boom, there's my maximum. Ta-da! So the question is, what do I need to do to justify that? Well, I still have to say that r prime of t is equal to 0 there, and I still have to make an argument either from critical points and endpoints or from the sign of r prime. But based on this calculator graph that I've got right here, it's really easy to see where r prime of t is equal to 0. That will be at a horizontal tangent, which is right here at this maximum. And it is also easy to see the sign of r prime from the graph. R prime is going to be positive when r is increasing, and r prime is going to be negative when r is decreasing, just like that. So coming back to here, we can take this calculator graph and we can immediately solve that equation, t equals 1.3630. We can justify it is a max because r prime is positive for t is less than 1.3630, and r prime is negative for t is larger than 1.3630. Yes, t does also equal 0, and it is fairly clear that because r prime is positive between 0 and 1.3630, that is not a meaningful candidate. We have a horizontal tangent, and then we go up. All right, so we don't have to consider non-meaningful candidates. Notice, again, I've said this before, but you cannot say because r prime changes signs. That's a local argument, and it is not what is being asked for here. We're asking for an absolute max.
And the well-labeled number line is not enough, it should be like what?
That's right. A well-labeled number line is a tool for helping you set up your argument, but it is not an argument. This, if I translate this into math, then I'm good. But other than that, it's just a picture. The picture may be worth 1,000 words, but it needs a caption. Okay. In part C, they ask us the total wait time for all the people in the auditorium. Now this question right here is confusingly worded, and so I want to put the wording here. All people in the auditorium is found by adding the time each person waits starting at the time the person enters the auditorium. And ending when the concert begins. The derivative of the function w models the total wait time for all the people who enter before time t. Pause right here. In all of this, notice that I have not yet been told to find anything. They're giving me information, but they're not actually telling me to find anything. The derivative of w is given by W prime of T equals 2 minus T times R of T. And now, finally, find W of 2 minus W of 1, the total wait time, blah, blah, blah. Okay, that's a lot of words. In order to read this efficiently, I need to figure out what I am supposed to find. And what am I supposed to find? And when I look at that W2 minus W of 1, and I see the information that is given to me, the information that is given to me is a bunch of stuff about how the wait time is computed, but also W prime. What do you see? Yeah, that's exactly right. So I don't need all of this background information to even solve the problem. All that I need to know is that the integral of a rate gives me the total change, the end. And I can integrate that rate because I have R of T, and I can integrate it directly on the calculator. Now, in this particular case, I've already entered that rate into the calculator. There we go. And so when I integrate, being careful to make sure I choose the right curve, notice I have to use the down arrow to get to my second curve here, and then integrate from 1 to 2, then my total wait time is going to be 387.5. Now, interestingly, the units on this are a little strange because this is found by taking and multiplying number of people times time. So what I get are people hours. Now that's a strange unit. But have you ever heard of man hours? Man hours reflect the total amount of time that everybody has to put into a job. So if a job takes 8 man hours, that means it takes 8 people 1 hour, or 1 person 8 hours, or 4 people 2 hours, or whatever. Well, this reflects the total number of hours accumulated over all the people that come in the concert. A total of 387.5 hours are wasted or socialized. And then finally, D, on average, how long does a person wait in the auditorium for the concert to begin? Now, this is an interesting question because it's ambiguous. On average, am I averaging with respect to the number of people or with respect to time? Because I can do both, right? But the average with respect to the information that they give or the direction they give, excuse me, is consider all people who enter the auditorium after the doors open. And that tells me that I'm averaging over the number of people. And so I can say that the average wait time, T average, is going to be equal to the total wait time, that is the integral from 0 to 2 of W prime, divided by the total number of people, which I already computed from the previous problem as 980. And when I go back and integrate W, not R, from 0 to 2, then this gives me 760 person hours divided by 980 people, which is an average of 760 hours. Sorry, 760 over 980 hours. That's what I meant to say. Does this make sense to everybody?